All right, so you can see my slides again, right?
Yes.
Great. All right, so today we are kickstarting our first session in the series where we are planning to cover one of the research papers or references that is mentioned at the end of chapter. So this is in addition to the discussions we have in our book club where we are going through every chapter of this book. And right now we are at chapter 5. So what I did was I ended up picking this topic, which was mentioned at the end. There were about like 40, 50 references for this chapter. And there were a couple of actually candidates that I thought would be interesting to, that can be a candidate topics for this session today. And I'll talk briefly about why I picked this one particularly and what are the other ones that I really liked in general, if you want to go and refer to that. So now, given that this is our first session where we are discussing a research paper, uh, I want to kind of point out what's the big idea behind starting this kind of series, right? Um, yeah, so my idea was that we are going through these chapters where we are covering the fundamental ideas. If we are also devoting time and if some of us can volunteer and, present a topic from the reference list in the book, that would help us connect a real world system design with the fundamental ideas in the book. Now, these papers or articles can be really deep. So I would kind of share it with everyone that let's not get discouraged by that, even if we don't cover the full paper. Some papers can be like, 10, 20 pages long and involve multiple concepts. So even if you can present a part of it and, tie it with the fundamental ideas in the book, I think that's really useful. Um, and then talking particularly about this topic, um, like reading the title of the, this article about real-time collaborating editing with Google Docs, and then reading the post about it, I thought that it's a pretty good article to even understand a system design, and it can become one of the questions in that area. So that was one thing. And then coming back to our original agenda about um, tying the concepts in the chapter, right now we are going through replication. So we'll see as we move along that this article really talks about replication architecture and conflict resolution strategies. Um, so that's that. And I would really encourage, people in our group in the book club session to really give feedback on, like today we have very low attendance. So I would encourage people to, give feedback on the time or of the content, whatever you think would be good for the group overall. So with that being said, let's start with the topic, right? So the topic we have is what's new with the new, what's different with the new Google Docs and making collaborations fast. So just looking at the topic, can you spot a connection between it and, replication idea? Anything that comes to your mind, like how are these two connected? And you don't have to like literally think about replication chapter, but in general, knowing the technique of replication, right? Where we are having multiple copies and synchronization, all that. What do you think would be some commonalities between this topic? Like how does this topic tie to the idea of replication? Any thoughts on that?
I'm not sure like what database and all that is involved, but just like a document needs to be shared among different people, right? So just maybe the data has to be, kind of presented on all these servers
Right.
at the same time, or with minimum lag, and
Exactly.
it shouldn't be like someone is writing a line and, you know, you are probably like overwriting it or something like that. So those kind of
Right.
issues might happen. So the data
Exactly.
flow, so that's just a thought about, but don't know what databases are, or, you know, which database is involved and how it's handled. But
Yeah, I think so. So you captured the essence of, you know, the commonalities they share, and we'll start with not just, you know, let's not focus directly on database, but like you said, you know, in terms of general concepts, you're right, right? Like first, we are looking at multiple, you know, if we look at Google Docs, how we use Google Docs. If I have shared a document with someone and two of us can be making changes, so we need some conflict resolution techniques, right? That's what we are going through in the book these days. And also, given that it has to be real time, so we really have to come up with approaches that can reduce latency, right? We don't want a very high replication lag. And the other thing is, I talked about replication architecture. So this is a little specific to the, you know, terminology that we are going through right now in this book. So we talked about, just to give a brief overview, right? We talked about single leader approach, where all the writes are coming to a single master node, and then you have other copies of nodes which can serve reads. But for writes, you have a single leader. And then there is a multi-leader approach and leaderless approach. So this Google Docs is looked upon as a multi-leader approach, where let's say I have shared a document with someone, with one person or two people, then all of us who can edit the document are looked upon as leaders, because we can make changes at our own end, and then they have to be synchronized together. There has to be a central server that kind of coordinates all the changes, and you are able to see a consistent copy. So yeah, I just thought it's since our motivation for covering this, you know, references is to see the connection between the chapter topics. I thought of, you know, kind of highlighting this. So that's where this topic is connected to replication. Now, I referenced a lot of articles and this talk specifically, which is of course by Martin Kleppmann himself, where he talks about these concepts. So I'm capturing screenshots from some of them because I couldn't find a better way of explaining this. So what happens with collaborative editing, right? There are three major goals. So the first is he talks about eventual delivery, right? So you're having, let's say, two editors, two people editing a document. And let's say the network connection for me went down, and there, you know, I come back after an hour. Eventually anything that's happened, you know, um, that has been propagated to the central server, every operation eventually should be propagated to every editor. And he talks about this asynchronous concept, which also makes sense, right? Because if a node is down and when it comes back, so it's not like every operation is delivered in, you know, same order as it happened. So because of the online offline nature of the clients, uh, the communication can be asynchronous. So that's point number one. The second thing is around convergence, right? If overall the two clients that I'm talking about, if we made together, if we made 5 changes, right, then what we want is eventually in any order, like the algorithms should be such that when changes are applied, both the clients should have end up in the same state, right? It shouldn't be that it is dependent on the order of operations and so on. And third, last but not the least, you know, it doesn't make kind of sense to lose data. Um, Reading the book, you do come across an algorithm called last write wins, which is a data lossy operation. So that kind of tells me there might be some applications where it's okay to kind of, you know, lose data and then, you know, resubmit the same operation again. But in general, when you're especially talking about things like, you know, these collaborative editing, it would be very frustrating and, you know, won't really serve the client if they end up losing their data, if one of the clients end up losing their data. So this is the, general properties that we aim for when we talk about collaborative editing. Now so when you read this article about Google Docs, right, you can think of this whole algorithm, the way Google Docs work, in two parts. One is this technique called operational transformation. And the third is the communication between clients and central server. So let's kind of break it down, why we need these two techniques and what do they do, right? So if you look at, right now I have just put as definition, but we'll see examples and then all of this would make sense. So the idea is that you have two clients who are working on their local copies, and they start with a common state, right? Let's say you start with an empty document, or you start with a copy of the document which is consistent, and both the clients see the same document. But now they start making changes and their states have diverged, right? So what this technique does is, it's a way to kind of resolve the conflicts, and it does so in a way such that no data is lost and both the clients will end up in the same state. And the benefit we'll see here is that when the clients are doing concurrent edits, it won't really block one client and make it wait for the other. So this is just a high level, description of it, but let's kind of go through an example to see really what it means. So I'm starting with a very simple example that Martin shared in his video. So let's say there are two clients, right? Each is starting with the same set of data here. And then client A makes this change where he adds a letter L, and here the second client adds this exclamation mark at the end, right? So now these are done at their local ends. Now what happens is, now let's say let's say client A sends the update to the server, right? Insert L at position 3. So what server will look at this is, and it will kind of propagate that change to client B. So, I mean, you can look at it in in multiple ways. Let's start with this one, that both the clients send their updates to the server, right? So both the clients send their updates to the server. And what server will do is, it will, let's say randomly, I mean, in our example scenario, let's say it first applies client A's change. So it will say insert L at position 3. And now, because of this operational transformation, it will say, it will be able, so this is an example of operational transformation, that it is able to detect that both, if it has to apply both these changes, then it has to adapt this, these messages. The next version that it sends to both the clients, you see how it is, like this message is changed because when L is inserted here, this had to be shifted to accommodate that insertion. And then at the end, both the clients are in the same state. So is it making sense, or am I going too fast?
I think so, yeah, this is okay.
One thing I'm little confused is it could be also a single leader thing, right? That so the server is single leader and he's getting 2 requests from the client instead of just taking one of them. The server is merging the request.
So are you saying that we can look at it as a single leader replication?
Yeah, as a single leader. And so generally in single leader, what we have seen is that if I'm reading some data, if 2 people are reading a data, let's say the data was A, right? And now I have modified AB, other person has modified AC, and then I'm sending server the modification.
Yeah.
The server will pick one of them and it will return success to one of them and failure to other, right? But here we can say that server will take the request of both the people, and instead of rejecting one of the requests and accepting one, which is instead it will just merge both the requests.
Exactly. Yeah, that's a good point actually. I did think about it, that why it's not leaderless, but you are right that it can be looked upon as a single leader as well.
But the thing you mentioned is because they both modify the same data, so
right.
the server will pick one. This
But
one is
single leader,
not
that would be in
modify
a
the same
traditional,
data.
that would be in a traditional single leader approach. That is one of the ways of handling, but that gives data loss, right? That's what we were saying. But this Google Docs doesn't do that. It actually has an algorithm where it looks at both the changes and then comes up with a, you know, updated message that preserves both of the changes.
And by
No,
the
but
way,
let's suppose that the first one say insert L at 3, and the second one say insert A at 3. Then the server have to decide which one to take.
no, it will merge. It will put A and L, right? That's what happen in these editors. That if you are saying if at same place, if I put the same thing, it will combine those two. So it will put A and K both. I don't know like what it will put at the first position and what it will put at the second
It
position.
will create a
But
list sort of thing too.
yeah, but that's fine. It will just merge the things. And so Dippy, you said in single leader, it will lead to data loss. It's not, so data loss happens when I'm returning success to both the people, but I'm keeping the data of only one of the persons. That is a data loss. But if I
You're
am,
right. No, but
uh,
you're right. So you are saying rejecting, like, you know, the
yeah, in the response I'm rejecting, then it's not a data loss. In the response, if I'm rejecting one of the requests and just succeeding one of the requests, then I have informed the client that I have not saved
correct.
your data, I have failed. So that is not
No,
a
you're
data
right.
loss.
Yeah. Thanks for correcting. Actually,
Yeah.
I kind of in my mind I was jumping ahead into the
Yeah.
different approaches. But you're right that, you know, the first approach is like Abhishek said. If you just say, you know, return failure to a concurrent, you know, modification or thing that's happening by another client, that's one way. But that's not also a good customer experience. And then the second thing is if you overwrite, right? Last write wins. That's definitely a data loss. So that's not what you want. So this is an approach where it takes care of, you know, combining and taking care of resolving changes.
So let me add this. Well, let me modify this way. Okay, let's say L. Say the first one say insert L at position 3, right? The second say just delete at position 3. So the server have to decide to do something because otherwise at the end
No.
who
So
will be the winner.
yeah. So Leon, if we take that also, right? So if you look at the algorithm, right? Let's say you start with this, insert L at 3, and this one says delete O at 3, right? So instead of doing this exclamation mark, you said delete O at 3. Now what will happen is when L comes in, right? And we'll see another example, like right now, I'm just showing a box for server, right? And I'm showing you how it accommodated both. But actually, if you go deep dive, you will see step by step. So if we take L at 3, the new string is this one, like hello, right? And then it will say, it has to, basically what client 2 is trying to do is it is coming up with HEL and this one is coming up with hello. So now if it tries to delete 3, O at 3, it can't delete directly at index 3, but because this has shifted now, right? So it will come up with, according to me, the final string will come out to be HELL. Is that right?
Yeah, but like depend on whatever the take first, right? If they delete
Exactly.
first or insert first,
No,
it's
so
up to the
that
server.
is a good point, right? Even if it picks in any order, that is the property of this. Let's say it picks deletion first, right? In that case, it is left with HEL, right? And then it picks up this one, insert L at position 3. Even then, it will end up with the same state. So that is the property we talked about here, that no matter what order operations are applied, eventually they should, they should be kind of eventually converging to the same state.
Yeah. And also when you're saying it's a single server, so if we have two users, like they are geography apart, like different geographies.
Yeah.
So will still a single server be feasible solution?
Yeah, so that is actually, I had a point at the end of this,
Okay.
because Martin talked about, this single server and stuff. I do have some, discussion points, which I also need clarity. Maybe we can pick that up then.
Okay.
Yeah, just briefly, like what I remember is there is this operational transformation algorithms which always go through server, but there are CRDT algorithms
Yeah.
which he has appreciated more. There you don't need a central server. There you can just talk peer to peer and resolve things.
Okay.
Yeah. Actually, that's a good point, because I did cover, kind of touched on CRDT in the future slides, but I somehow didn't look at it that way. So that's a good point. Yeah. But I was curious about, what if instead of making this as a single point of, avoiding this single point of failure sort of thing, right? If I add two servers for this cluster also, I mean, it's more of a,
Correct. Yeah.
that can be another question, right? How that will work. But just like any distributed problem, it will, need to be handled in a different way. But yeah. But does this idea make sense overall so far?
Yeah.
So the point is this technique, operational transformation. Like it says, I put some text here after showing this, hoping that this would make more sense. So the idea is, if you start with the document, which is consistent on all the clients, and if you make some changes to them, and then, so what server will do is, it will come up with new operations, so that if it picks a operation from, like Leon was saying, if I pick client B update first, and then try to accommodate A, it will preserve both, regardless of which update I pick first. So that's what the definition here says. Now let's, so this is what another thing that he mentioned, that if you look at this idea of, conflict resolution techniques, there are, multiple algorithms and techniques available. And this Google Docs actually comes under the family of Jupyter algorithms, and it's based on the central server idea. And then there are other techniques which are more memory intensive and requires tracking history in an n-dimensional way, which are much more complex. But I mean, just to give a perspective on where these, variety of algorithms fall, this was just a quick idea. It was interesting how this whole, concept actually came out in '89. And so it's not like it's just a breakthrough or new, idea. I don't know, like, just we can quickly go to another example, or this should be hopefully easy to follow given the previous example. So here we again have two clients which are starting with a consistent state, and client John makes some changes where he deletes, where he changes the last three characters from 1 to 3 to ABC. So there is a set of operations that are recorded. And similarly, as this client is making changes at his end, another client starts making changes, and what he does is he tries to add some text at the beginning. Well, I change it. Basically, the example here shows only 2 characters, so it's not just 4 characters here. So basically, this client tried to add 2 characters at the beginning. Now, think about that. If this client directly picks up the changes of John, what will happen is it will pick this change, delete 9 to 11, and it will end up changing the text to this one, which is, incorrect, right? That's not the change that was intended. So that's why we need a central server which can look at the changes of both the clients and it can apply this operational transformation. So what this technique will do is, Lewis will look at this change, which was 9 to 11, delete 9 to 11. And because it can see that, okay, I added 2 characters in the front, so I have to shift them, right? So this basically this is happening like at the server. So then this change will be sent to Lewis instead of 9 to 11. And I mean, not to confuse you with very specific like details here, we can refer to the slide deck later. But if you capture the main point, that rather than sending a raw change to your peers, what you're doing is you're having this central server which can actually take these changes and look and send an revised or transform change based on the client's copy. So this is another example of operational transformation. So because we inserted 2 characters in the front, we shifted our deletion index. And yeah. So this was an example of operational transformation, which basically helps you um, preserve the changes from multiple clients. But now let's also talk about in this article that we are referring today. This article also talks about what will happen when a client sends a change to the server, and let's say because of some network issue, server has a delay, right? Server can't acknowledge that change. Like, how will they collaborate? What would be that protocol look like? So now this is going very specific into, this how Google Docs work. Um, it's kind of interesting to know about how they come up with this technique. But personally, for me, when I was reading this, I was trying to capture the high level idea and not to get lost in the details. So here, if we are looking at this protocol, communication protocol per se, so what they're saying is you have 2 entities. You have your clients, right? End clients, and then you have your central server. So at client, I'm tracking 4 different types of information. One is what is the most recent version that is sent from the server to me. Then any changes that I have made locally, but I have not sent it to server. The third is the category where I have sent my changes to the server, but I haven't received acknowledgement. And the fourth one is what is my current state that, of the document that I can see. Similarly, server also keeps tracks of, few bits of information, but let's go through this as an example. Otherwise it's all text. So here we are seeing 2 clients, Louis and John, and you have a central server. So as you see here, if you look at this box here, we are tracking 4 bits of information as shown on the slide last time before. So we have a revision, like a version. We have a list of our pending changes. So this, and then pending changes would be the changes that I make locally, but I haven't yet sent them to the server. And similarly, sent changes would be the ones that I have sent to the server. Current document is what the current state looks like for me. And similarly, on the server side, we are tracking 3 bits of information as shown here. So that's the data structure sort of to look like for both the entities. Now, if we start with this client, right? Let's say this client, and the examples that I'm showing here would be very similar to the previous 2. So this is more like reinforcement of the idea of operational transformation. And yeah. So what we are saying here is, let's say the first client inserts hello, starting from position 1, right? So it hasn't sent that change yet to server. So it's in the pending changes, and that's my current state. Now, at this point, I send the change to the server, and the server gets the change. It hasn't yet sent me the acknowledgement. So that's where we are. And now if you see the server current state is hello, like it has applied that change locally on it. And meanwhile, what happens is Lewis also inserts another word, world, starting from index 6, because the word hello was, 5 characters, and then it inserts world at next index. So similarly, you see how these two, pieces of information are landing in pending and sent. And at the same time, when Lewis inserted the word hello in his local copy, the second client inserted exclamation mark. Like right now, if you notice, the change that Lewis made, the word hello, was only propagated to server. It hasn't yet reached the other client. So this client is just trying to insert an exclamation mark as the first character in its local copy, right? Now what happens is, yeah, so Lewis change here is, in the pending list because it hasn't received the acknowledgement. And yeah, that's why we have gone through this. Now consider the case that at next moment of the time, so the server sends an acknowledgement that yes, I have received hello to Lewis, and only then Lewis can send the next change. So that's kind of the protocol Google Docs follow, that it's cannot receive the next pending change unless it receives the acknowledgement for the first one. So it waits for that, and then it parallelly also sends the change hello to the second client. Now this is where operational transformation comes in, right? If you remember that the second client had a local copy with exclamation mark, and now it got this update that, hey, there is this word hello starting from position 1. So it knows that it has to shift this exclamation mark to position 6, right, by 5 characters. And that's where this idea comes back, operational transformation. I mean, you may be, I hope this is kind of, making sense. I added the text so that if we have to refer later, it makes sense. But the essence of this is the data structures that are used. What kind of information do we need to keep at every client or every server or the central server? And I would take this kind of information also as if somebody were to go to a system design interview. I think this is a good thing to keep in mind, that what kind of information I would keep at every entity. And yeah, so this is the same technique, operational transformation. This is going deeper into that. All right, right now my document here is hello with exclamation mark, and this the left client, like Lewis, is seeing hello world locally, right? Now at this point, this comes to when so yeah, so at this point, both of them send their changes. So the left, Lewis, sends its change that, hey, I'm inserting the word world at starting at characteristics. And then John also says that, hey, I'm inserting exclamation at the same position, right? So this comes back to the scenario we were discussing before, that both are talking about the same position, right? Then how will it resolve it? So what it will do is, in this example, it's saying that, let's say it picks this change first, and you can repeat the same algorithm by reversing the order. It will land in the same same case. But let's take the case when it applied this one first. So it applied this and it moved it to revision log, and it sent an acknowledgement here, and then it sent that change to this server also. And again, the operational transformation idea comes in, and it adapts the transformation, and it knows that it needs to come up with this final string hello world. Yeah, so this is the idea here, that both the clients eventually end up with a consistent copy of the document containing changes from both of them. In the first shot, I don't know, like this figures can be a little, hard to follow right away if you're finding it confusing, but let me know if you want me to explain anything again. Um, but that's the essence, like how the transformation is done, and yeah, the data structure, idea of data structure.
Yeah,
That's
only one thing, just curious to know, when is the revision updated in this case? Only when he receives the acknowledge from the server?
right. So when the server actually sends the, yeah, that's a good question. So here, when you see here, right, like when the first acknowledgement, it's more like a server global, revision number. So
Okay.
server comes up with this revision number, and that's where it updates it, like from 0 to 1. And similarly here. Yeah.
Okay. Yeah, I think it was good actually. Yeah, could follow all that.
So, so this was about, like, when we are talking about this collaboration model. What's interesting, if you notice in this model, is the amount of information that is sent over the network, right? It's kind of differential. Like, it's only sending, okay, what needs to be inserted or deleted and at what position, right? It's not like sending the whole text, like hello world or something. So the amount of information that is sent is the bare minimum needed. Then any editor can basically apply their changes without waiting for server to acknowledge those. And why we say that is coming back to this data structure. So we saw in this case how, like in this case, when it sent a change, hello, and it had not received an acknowledgement, it just can move that information to its send changes and continue with its local updates. So it doesn't really have to wait for like uh, acknowledgement before applying another change locally. That I wasn't very sure of the last 2 points. Like, at the surface of it, I see they kind of make sense, but I didn't really like the first 3 points were pretty clear to me. But like the fourth point says collaboration complexity is constant. So it's saying that as you add more clients, the complexity of processing does not increase. I am given that I wasn't sure, like, if I were to think about it, that if I have like 10 people sharing a document and multi editing at the same time, um, like won't it really, for the synchronization, it may be because of this pending list and revision log that it won't really affect the like the time complexity or something, but I wasn't too sure about this, to go into this point in detail. Uh, yeah, and then the
Yeah,
last one, yeah.
probably it's like linear, like it will, what he means to say it is the complexity will not like exponentially increase or something.
Exponential or quadratic or something.
Yeah, yeah.
Okay, yeah. And the last thing is that both the server and clients are kind of, sharing a part of the, processing complexity. So there is a kind of a spread of the, workload.
So one question I have is, so in this like hello world example, right? If I have put exclamation first, like, I mean, if the exclamation reaches the server first
Yeah.
before hello world, then the server will combine it as exclamation and then hello world, right?
Let's see. So maybe we can walk through it. So you're saying at which point, like here, right? You're saying that when I'm trying to insert world at position 6 and exclamation at position 6, actually this one, like here,
Yeah.
right? So you're saying that instead of this first, and let's say if I go with this one, second one first, right? In that
Yeah.
case, it will apply hello exclamation,
World. Yeah.
uh, hello exclamation, and then accommodate the next, yeah, the placement of world.
So yeah, so sent world and sent exclamation reached at the same point, both are revision 2. So how had it resolved that which it should keep world first? I didn't understand.
Right, right. No, so yeah. So in this example, it's not like it kind of, there was an algorithm to say this was picked first. What they are picking a scenario where, let's say, if this reached first, then this, or let's say even if they reached at the same time per se, but it has to, let's say, pick one, right? Uh,
Yeah.
so what they are saying is, randomly they chose this one, but if it has to go other way around, I think the idea here is that uh, not necessarily coming up with the same output, but both the clients eventually should see the same data.
Same data. Yeah. Yeah.
Right? It shouldn't be like this is seeing hello world exclamation and this is seeing hello exclamation world.
Yeah. Yeah. Okay.
That's
So similarly, if like one client deletes a word, let's say hello was deleted, and other client has modified it to hi, right? So
yeah.
if then also it depends on the order. For one
Yeah,
particular order, it might delete it or it might keep the modified, but eventually they both will converge and they will see just one thing, right?
correct. That's
Yeah.
my.
Okay. Okay.
And actually, I was also thinking of there is this so this is what this algorithm is about, but there is also this parallel approach that GitHub takes, right? I was thinking that, let's say, I mean, there are so many examples of conflict resolution. I got curious about what we see on GitHub. So let's say somebody pushed a change on a master branch, and then when I try to push a change, if it's a conflict, right, then I get a message that I have to resolve conflicts and then push it. So I think so that's a little different one, but
Yeah, it's different because like in this words and all, it's fine. Like if it like if you put exclamation first and world or later, like you can see and resolve it, but it's fine. But in code, you have to actually ask the users
right,
whether the logic which the server came up with it's right or wrong. So that's why
make
if it's different files, then it's fine. Then the server will resolve it. But if it's same file, then it needs to confirm from the users that is that what they were expecting. So
Makes sense because it's more like if whatever resolution server is coming up with, right? Is it
yeah,
like something that can be okay if it came up with some wrong, it can be, revised later and
yeah,
it's like a big deal. But if it
yeah,
change, it can totally mess up things.
yeah. In code, it's a big deal if something is wrong. Here, it's okay. I mean, yeah, they
Right.
can fix it.
Right. So that's that. Now, in this talk by Martin Kleppmann, he talked about this. He kind of highlighted two issues with operational transformation, and he talked about this first one where he says, "Well, I added this last point, but I think that won't really hold true because this operational transformation technique was kind of by definition defined for a central server kind of architecture." So his point is, first of all, it's like a single point of failure, like Abhishek, you were describing earlier, coming to CRDT. That's one limitation. The other thing is that if you look at the way this thing was working, right? At the server, we have to kind of decrypt the whole message. Like if you are looking for some encryption, areas, scenarios, then this approach won't work because at server you have to end up with decrypting the message. And that's where he brought up this technique of CRDT. And the example he came up with this is this one. Um, so you start with this document, consistent document on both the clients. And then rather than like in operational transformation, what we did was we had this indices. And so before going into that, so you make a local change here and on both the sides. And then there is this idea of identifier, right? So whenever you make a change, you pick up the next identifier that's possible from this, list. So here you are till 3A. So the next identifier is higher identifier is 4A. And similarly on the right, you kind of, he talked about this idea that, to make them, to, to make them kind of globally unique, you follow this technique of appending, let's say, a brief, letter of the node name or something. So here he came up with the identifier 4B. So this was the change made on both. And now, well, as I'm reading this, so even in this case, he did talk about a server thing, but I have to go back to this. But yeah, so the way I thought was there is no need for decryption on the server. So you basically pick up your change, you pass on your change. And if you notice the difference here with operational transformation, what we did in operational transformation is you send the operation like insert L, and then you place a position, which is kind of, common to both. Here, the position, you're not send, so let me show this. So when you're sending this position, you're kind of sending an offset, right? Like at letters at position 6 or position 1. Whereas here, you are coming up with a new identifier for a position, and you're saying this position comes after, XYZ, or it comes before XYZ, something like that, right? So you don't give exact offsets, but you come up with new identifiers, and then you pass that information. So this is a very trivial example. I'm not going into details of this, like he covered use cases where this thing can also lead to, like insertions at the same point, deletions at the same point can lead to issues in this approach. But I'm not going into detail on this. But for me, the biggest takeaway of this CRDT was that the message doesn't need to be decrypted at the server. I think there may be more examples like Abhishek, you were saying, which doesn't involve like server, but yeah, I didn't, I kind of just added this as something I could read.
Yeah, even I also don't know. I just remember he was saying something like this, not sure. But here, looking at your example, it seems like this is also going through a server, right?
Right. I mean, this is like I just picked up from his only. Yeah.
Okay.
This is also going through server. It's just like, yeah. So, but yeah, if you're interested in, reading more about it in the book, he gives a very short description, like just 3-4 lines. But in his talk, which is the link here, he really goes detail about, what are the edge cases where this can fail and stuff like that. So, yeah, so this was kind of the end of the talk. I hope if, and it's kind of a pretty deep topic. I hope even in worst case, one thing that this talk was able to do today was kind of make you excited about go and check out his, talk where he explains all these concepts really well. So, yeah, so this is pretty much what I had today.
Yeah, definitely. It was really good. Thank you, Dippy.
Yeah.
Yeah, it is good. Yeah, thanks.
Yeah, I mean, yeah. Otherwise, this topic is really deep, and I think 45 minutes were not enough. But yeah, like going over the high-level overview of how it would actually work.
Yeah,
Yeah, makes sense.
right. I mean, it's
So,
interesting that at the end of the talk, if you hear his talk, at the end, like he presents so many, different examples and edge cases, and he, at the end, he says, all right, just believe that somebody has figured this out. And people know this stuff. And at this point, I give up. So I was like, well, if he's saying that, I believe it.
yeah.
Can you share that YouTube link?
Yeah, I have added the YouTube link, and I'll also add it in the, like the Discord.
Okay. Yeah.
So yeah, this is like about just the same, like an hour or 50 minutes talk, and he really explains it very well. So yeah, so that's pretty much what we had. Any feedback like on not just this topic, like in this topic, if you have feedback on how we should, organize Wednesday sessions, feel free to, start a discussion on the book club channel.
Yeah. So what's the, probably you can